the award. So Grégoire will say a few words about what's so exceptional about Philippe's teaching, and I probably agree with anything you will say.
Okay, thanks, Guillaume. So yeah, yesterday evening at 11 o'clock in the evening, Guillaume asked me to prepare something to say about Philippe, so I prepared a few things. So just to put some context, Philippe was my PhD advisor. So this is the Griffiths Award, is a teaching award. So in teaching, I also put mentoring, and I think Philippe has been and still is a great mentor, and this is why I really think he deserves this award. So just a bit of context. So Philippe has studied here a lot. He's not from here, he's from France, but not from here. But many people in France study Nancy. So Philippe had his geological engineer degree here in Nancy. He did a master in Polytechnique Institute of Lorraine, his PhD in the School of Mines in Paris, and then he worked at BRGM, the French Geological Agency, then in Guinea. Then he moved to Switzerland, because Switzerland is important for research, of course. He was at ETH and now at University of Neuchatel, where he's professor and also adjunct professor in Oslo. So he moved everywhere. And many of you know that he did a big impact in the field of groundwater, stochastic hydrogeology, been editor of many journals, groundwater, hydrogeology journals, advanced in water resources, and so on. So he's a great researcher. But I think this award is not, it's a teaching award, but often I've seen great researchers who disregard teaching. So I heard often, oh, I teach too much, I want to teach less. But Philippe is not like this. Philippe is really happy to teach. He's really enthusiastic about teaching. And precisely, he's a great researcher, but also a great teacher, and this is why he deserves this award. So to give some context for me, so I've been following his courses, but also interacting with him for years. Often, as a young researcher, I was coming to him and trying to formulate an idea, and it was messy. I couldn't formulate it well. I couldn't have my ideas clear. And no matter how messy I was in my explanation, Philippe would get it, whatever I was trying to say, and make it better. And then tell me, okay, this is what you can do, and then you can get a PhD from this. This is the great thing about mentoring. And also for teaching, I think often I've seen Philippe teaching, and then staying late at night, or after the class, talking to the students. And even now, so I'm in the University of Lausanne now, Philippe is in Neuchatel, and he comes to teach in Neuchatel, so I see him giving his class. And in the evening, I see him still there with the students, some students that still stay and ask questions. And the university is closed, everybody's gone. There's just Philippe with the students, and he managed to passionate them and keep them there. So I really think he deserves this award, and this award is made for people like him. Okay, thank you, Philippe. Thank you.
Merci, Grégoire. Thank you, Grégoire. This touches me quite a lot because indeed we spend a lot of time teaching, and in research we are evaluated mainly on research, on papers, and etc. And there is a kind of schizophrenia between our daily life and what helps us to grow in university, in academic in general. And I think if you think that I am a good teacher, it's also because I had good masters. And I had good students. And here I want to thank all these students and the masters, and some are here. I'm very happy that Jean-Laurent Mallet is somewhere here, because there are not so many professors. I don't know for you, but for me, there was not so many professors during my academic life that really motivated me and kind of sparked ideas and said, okay, you can do something, and this will be fun, and you will have passion on that. And Jean-Laurent was one of these rare people who were really so passionate about what he was doing that he was an example. And Guylain de Marcilly was maybe the second one, and Albert Tarantola. So there are not many people like that we remember. So I want to thank all these persons, mostly my students, but also some of my professors and colleagues who participate in the work that I will present today, and also the sponsors, so the Swiss National Science Foundation, Total Energy, who funded some of our research, as well as Ephesia Consult. There is Philippe Puyot here, and Joe Variance, who is also taking over now. And the IAMG for getting this wonderful prize and organizing that and inviting me. So the topic of the talk today is really An old thing that everybody knows in earth sciences, and that is a major issue, it's interpolating, the interpolation problem. So we have data and we want to interpolate. And to give an idea, a framework about this interpolation problem, I will take one example, which is a contaminated site in Switzerland. And here, okay, it doesn't look so big or so important. In fact, to clean up this site, they had to spend 1 billion Swiss francs of analysis, boreholes, decontamination. So this is a huge expenses. And to do the decontamination, you need to know the underground, where the contamination went from the waste disposal that is here in the aquifer below. So they drilled a lot of boreholes to characterize the geology below the waste disposal. And this is one of the sites in Switzerland where the density of boreholes is the highest because of this problem of contamination. So I made a rough calculation. I estimated the volume of rock that has been sampled with all these boreholes. So you see there are 170 boreholes, and the volume that is sampled is around 200 cubic meter. And if you now compute, basically you make a square, you evaluate the volume of rock that you need to characterize. So if you want to know the pollution, you need to know in every cell what is the contamination, you need to know the rock properties, you need to know the porosity, the permeability, and it's not a big domain, 150 meters by 400 by 70 meter deep. It's 24 cubic million, meter cubic million. If you make the ratio on an image like that, where you have 200 pixels by 450, it would be like you have 4 pixels. So it looks a lot, but in reality, we have a ratio, we have a quantity of information that is really little. So now, from these 4 points, we want to know everything in this square on this 92,000 pixels. So basically, we always talk about big data, machine learning, and etc. But we are in the black. We are in the world of small data. And you don't see it here, but these are our data. And usually, they are misplaced. They are not where you need them. So we need to make, to be intelligent and to interpolate in a manner that is, that makes sense. So we have to add prior information. We cannot just interpolate from the data. If we don't add prior information, we have no idea on how we can interpolate the underground properly. So during many years, the classical geostatistics was using a prior that was simply that all the relations in space could be modeled by a multi-Gaussian distribution like this one. And this was convenient because we just had to estimate some mean values, the mu, and the covariance matrix. Maybe we can make it with a variogram that just depends on distance, but we could estimate all the probability, the conditional probability with this kind of expression. And that was a prior. That was the prior that we were putting in our interpolation in all our basic geostatistics. But then we are in 1990. I am here in Nancy, and Jean-Laurent Mallet, I think it was in 90, invited André Journel. And at that time, he gave a seminar. We were in a small room. We were not many people. And André was very excited about indicator simulation. He gave this seminar, I remember very well. I did not catch everything about the indicator simulation, but that was the things that they were doing at the moment. I think Jaime was also in Stanford at that time. But then they were thinking, they were presenting all the sequential indicator simulation, all this work on simulation, but they were in fact working and thinking on something much more exciting, which was multiple point statistics. And the idea of André, that was also covered by Mohan Srivastava and others, was that we need to formulate the prior information that we have. If we are interpolating something, often we know what we want to interpolate. We know what we expect. We know the type of interpolations that we want to do. And so they came with 3 radical, novel ideas, which were the punctual data are not sufficient. They are here, they are important, this is our data, but we have to complement them by something. And this something was a training image. So here you have one. Do you see my pointer? No. Maybe the battery is low. Okay, but you see the training image. That was a sandstone, a picture of sandstone in a crop. And if we want to interpolate something or simulate something that looked like that, we will never do it with a variogram. That was not possible with a simple variogram model. So they need something more advanced. And 2-point statistics were not sufficient. So they had the idea that we should have multiple point statistics. So looking at the probabilities of having complex patterns in Now I don't know if it works better. Okay. And if you start having these multiple point statistics, the combinatorics is huge. So you cannot have a simple analytical model. So we have to replace this by a non-parametric approach. And that was the birth of multiple point statistics. And the first paper was published in '93 by Guardiano and Srivastava. There are wonderful papers about the history of this thing by Mohan Srivastava. If you're interested, I can point them to you. So next slide, because now I don't have even the... Merci, Guillaume. And the breakthrough, the technical breakthrough, so all these ideas were nice. They could start to work, but the computing time was huge, and it was not practical. So then came Sébastien Strebel, who did the first implementation that was efficient for multiple point statistics. And here you see a nice example from Sébastien, where on top you have the true image, top left. So this is the underground, you don't know it, but you have some samples, so you have some incomplete data, which are the points on the upper right. And below you have a structural model, which is your training data, your training image. And based on that, you can derive some special probability, multiple points special probability, and combine the incomplete data with the probability model to get one simulation. So this was SNESIM algorithm, and that was a real revolution. And then a lot of people got excited by that and started to jump into this field. And now in 20 years, so that was about 20 years ago, and in 20 years, there was an explosion. A lot of people got excited and created improvement, modifications of this algorithm, and we have been in this world developing algorithms, and it's a mess. Now there are too many papers, I cannot read all of them, but there are different philosophies, different implementation details, and I will not go into that. There are some papers that try to review this. There is the book by Grégoire, who also makes an overview of this. So there are sources for that. I will not go in that direction. Instead, I will show you our algorithm, the direct sampling, and I will show you how it evolved over the last 10 years. So our algorithm that was developed during the PhD of Grégoire is nice because it is so simple and stupid. So you will see in 3 slides, you will understand everything about multiple point statistics. So the idea is that you have a training image, training data. We want to simulate something in space, to interpolate something in space that looks like this very rough image that you have on the left. So this is supposed to be a vertical section with channels and maybe some clay plug at the bottom. You can imagine that. On the right side, you have a small simulation grid for illustration purpose, where you have some conditioning data. You have measured some geology. These are the blue and 2 yellow points. And now we want to simulate, to fill all this grid with values that are in interpolation in this grid. So what do we do is really stupid. Huh? We go into the training image at a random location. You see the red square here. And we check around the data in the simulation grid, where are the existing data, the conditioning data. We call that a data event. So in fact, it's a vector. It's a vector where you have codes for the green value at a certain position, blue value at another position, and yellow value at another position. So you have a vector with only 3 values, 3 codes. We go there, we retrieve the same locations, and here you see that they do not match perfectly. You have blue, blue, yellow, and we want yellow, blue, yellow. So there is 1/3 which is wrong, so I can represent an error of 30% for this first iteration. Now, I'm stupid, I just go next in the image, and it will be a little bit more complicated because we have to make a pass, but we simply move this point and check another location. And here, what is the error? Yellow, 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 again, 1/3 is wrong. So the error is again 1/3. So I have to go somewhere else. Boom. Aha! I found something interesting. Here it's good. Yellow, blue, yellow, yellow, blue, yellow. So what do I have in the position unknown? Here, I have a yellow. So I'm happy. This is a compatible pattern. We have two data events. They are similar. I can take the value here, copy and paste in my simulation. And now I go to another location and I repeat the process. So what we did, what we did was to define a distance between two patterns. So we have the pattern on the simulation grid, the pattern on the training image. These are two vectors. We compute a distance, which is simply the proportion of nodes that match. And we scan the training data set until we find the first data event that is below a threshold. Because life is never perfect. You never find exactly what you want. So we have to accept a little tolerance. So we define this tolerance. And if we don't find something that is below the tolerance, we stop after a certain fraction. If you have a huge training data set, millions of cells, you don't want to spend your life searching without hope. So you have to stop somewhere. So after a certain number of iterations, you say, I take the best that I found so far, and I'm happy with that. So if we now look at a simulation, I will try to do it there. Okay, so what I wanted to show is that at the beginning, so this point will move in the simulation grid according to a random path. We will scan the training image, and every time we have just defined the number of nodes that we want in the search in the data event. So what you see in the beginning of the video is that the search pattern is very large. It covers almost the whole range of the grid, the simulation grid. So if you see, stop here, you see we want to model the blue location. The blue location, and we have conditioning data that are on the other side of the simulation grid. So we have to search for a very large pattern in the training image. And once the simulation progresses, there are more and more conditioning data that are added to the simulation grid. So you start filling this grid, and the search pattern becomes more compact. At the end, it will be only the neighbors around, you see the points that we want to simulate. I guess now you understand the principle. So direct sampling is a technique that iteratively sample the training data set, but with condition. So we don't sample it randomly, we make conditional resampling of the training data set. Of course, the idea is stupid. You can program it in just a few hours. The code will be slow. So all the details are in how to optimize the search, how to be efficient in scanning properly the training data set in a clever manner. And here there are plenty of tricks, and this is the main work of my colleague Julien, who is somewhere in the room, which you have seen that he is the co-author of this work. The nice point, there are drawbacks with this method, the time, but the nice point is that it is super flexible. And this is what I want to show you now. Because we can adapt the way we compute the distance, we can adapt the acceptation criteria, and we can open many doors and do a lot of interesting things with that. So we can simulate continuous variables, we can condition by inequality, we can make multivariate simulations, we can do simulations with non-stationary training data set, support effects, etc. So now I will show you, illustrate these ideas. So how to move to continuous variable? Super simple. We just changed the distance. Before it was a proportion of mismatching pixel. Now it's just a distance between two vectors, a L1 distance between the conditioning data and the data in the training data set. Easy, we normalize it, and the rest is the same. So illustration. We are hydrogeologists. We do applications in the field of groundwater. We have a nice site in the Swiss Alps. It's close to Les Diablerets. Maybe you know this place if you know the Alps. There is a glacier on top of a karstic aquifer. The glacier is melting. We want to know about the evolution, future evolution of water resources that are used for a city, Conte. So to know that, we need to know the amount of ice that is there on this glacier. And this amount of ice was not known precisely, and it is evolving fast with climate change. So we wanted to estimate the volume of ice. So how to do it? I mean, volume of ice is super simple. We need the top surface, and for that we made, Grégoire gave us his drone for a few days, so we made a few flights, and we measured the topography of the glacier. This is what you have on the left. Now we need also to interpolate the bottom, and this is where it comes a little bit more tricky. We still use the drone to measure the topography of the exposed bedrock where the glacier was 100 years ago. The glacier is retreating. Now we see what is below the glacier, and this is what you have on that image. To have a few points below the glacier, we went on the glacier and walked with a radar, ground penetrating radar. You see our tracks on the left here, where we have been walking, and here you see the cross sections in two-way time. So this here we can pick the base between the ice and the rock and transform this in depth. And now we have a series of points on this image, and we want to interpolate. And this is a nice example because we have a lot of data. And so we said, okay, that could be a nice thing to show the difference between traditional geostatistics and MPS. So now we did both. And here you see one simulation of MPS on top, one simulation with sequential Gaussian simulation below. From far away, they look the same. Huh? You don't see much difference. Here, for the Gaussian simulation, sequential Gaussian simulation, you need to infer a variogram. I don't show you the details. But for the MPS, we take the exposed bedrock map as training image. And here you see cross-sections through this glacier. And you see the evaluation of the uncertainty with an ensemble of simulations with SGS on the right and MPS in the middle. What do you think? I mean, this is very, very close. Huh? It's a little bit smoother for MPS, but uncertainty reduces when we cross some data. Huh? You know, we have these lines where we have been passing away. So when you cross a line where we have data, the uncertainty diminishes. But globally, it's the same. Now, if we look at the volume calculation, kriging, I don't show you the kriging, but kriging gave us 109 million cubic meter. Okay. SGS, the same. MPS, more or less the same. So everything is consistent. Calculating the volume is a linear operator. Calculating the mean of the volume on an ensemble of simulator gives you the same as the kriging. So if you just want the volume, kriging is fine. The uncertainty was also roughly the same. You see SGS and MPS, 1.5, 1.7 million cubic meter. No big differences. Okay, so here you say, why do we care about MPS? The difference comes when you look at the morphology of the bedrock. And to illustrate it, if we look at the morphology of the bedrock below the glacier, we computed what is called flow accumulations. So this is very standard in all the GIS systems. You compute how much cells are upstream a given cell, and this gives you numbers. You have this grayscale with the flow accumulation. And what you see, we computed that on the exposed bedrock, and you see this structure of accumulation. And if you do it on SGS, it's much more noisy. And so there are no big accumulation. The surface locally is much more roof. On kriging, you have these long flow accumulations because the surface is very smooth. And with MPS, we are the closer to the exposed bedrock. So we made some statistics to confirm that. So why is it important? Can you guess? Because if we want to compute the movement of the glacier, if we want to model the glacier, the roughness of the glacier of the bedrock below the glacier will be important. So the prediction of the movement of the glacier should not be the same if we do SGS, kriging, or MPS. So this shows you that, one, MPS is consistent with SGS and kriging. That gives the same kind of results when we have good control. But we get more with MPS. And in a way, it's easier because we don't need to do all the fiddling about estimating the covariance and etc. So that was just continuous variable. So simulating surfaces led us to think about inequalities. Because there are many situations when you model geology where you have inequalities. You drill a borehole, you don't reach the base of the formation, but you know it's deeper. Or you have an erosion surface, you see a strange contact, like in well W2, and you know that if you want to interpolate, this surface should go higher, and then we will erode it. So there are many situations in real life where we have this inequality, we know this inequality, and we have to account for it during the interpolation. In standard geostatistics, this is feasible, this is well known. In MPS, we can do it now as well. So what we do is just to adapt the distance. And what we do is, when we have a location like here, this X1 position, we have an inequality here. We will look in the training data set for an equivalent pattern. And in location X1, for example, we know that the value should be higher or below something. In the training data, we find the value, and we will compute the distance and say it's 0 if we are right, if we are in the right interval. And if we are not, we compute the distance to the border of the interval. And that's it. And all the rest is similar. And I show you a result again by simulating topography in central Switzerland. We have a data set, we create some minimal bound, maximal bound, and I just show you a section through the simulation. So here you see simulations without inequality. You see in blue the reference, the real topography in the Swiss Alps, in orange one realization, and in gray an ensemble, the range of simulations covering this ensemble. So if we put now the purple line on top here, which is an inequality, you see that all our simulations will go below, and all the simulations will be pushed down to the... And if we make an interval, that will work as well. So now we can do that. I'd like to check the time. I have so many things to tell, so you may have to stop me, Guillaume. Sorry. Now we have to move to multivariate simulations. So for the moment, we had only one variable, categorical or continuous. In reality, in practice, we often have an ensemble of variables that are of interest for us. The most obvious case is in remote sensing. This is the coast, the southeast part of Australia. This is for Malcolm somewhere. And you see different variables that are measured with remote sensing, latent heat, soil moisture, surface temperature. And they have complicated relations between them. This is not linear. This is difficult to model using transformation and etc. With MPS, we can take this as a training data set and just have more distances. So we will have a pattern. We will have all the variables. So we define the number of neighbors for each variable. We define a distance for each variable. And we define a threshold for each of the variables. And the rest is identical. So you see the generality. Simplicity means generality. So basically, on the left side here, we want to simulate a multivariate situation. On the right side, we have a training data set, so you have all the variables. And when you want to simulate one variable at one location in the grid here, you have a kind of nested pattern where you know the other variables around this point, and you know your variable, and this is in space. And so we are looking for similar situation in the multivariate training data set. So this was identified almost since the beginning of direct sampling, but this is very strong because it opens a very wide range of applications. And I will show you some examples now. So the most simple, the basic one that we did early was to, when you have a training image, so this is the Roussillon aquifer, again, hydrogeology, south of France. We want to model the heterogeneity in this aquifer. And we have a concept from the geologist, and the concept is upstream here. This is this training image. So basically, they say that we have alluvial fan on the upper part of the aquifer. Then there is a transition with braided systems, and then there is more meandering belt channels on the downstream part. So this is the concept. Maybe some crevasse plays as well. But the training image is non-stationary. So if you want to apply MPS, if you don't do anything, it will start mixing up all these elements and putting alluvial fans in the downstream part. So this is not good. So what we simply do is we add a second variable, this is variable 1 here, that represents the distance between the sediment source and the coast, so normalized between 0 and 1. And then on the simulation grid below, we will interpolate this distance. The cost is 1, the upstream part is 0, and we can play with the interpolation here. We will give orientation to deform the channel, and then you get your simulation. So here we simply used this multivariate framework. No need to add anything more. We just have the training image. It is non-stationary. We add a variable that describes the non-stationarity, and then we use it for conditioning. And that's it. So this is a bit simple. We can make much nicer things with Alexis Neva, who is also somewhere here. He spent a month in the field collecting, this is an aquifer in Switzerland, in the upper Ahr Valley, just between Bern and Thun, close to Interlaken. Maybe you know the place. And there is a large alluvial aquifer that we want to model because water resources, geothermal exploitation, gravel exploitation, etc. So it's important to characterize the aquifer. So we went in the field, collected a lot of transient electromagnetic data, and after a month, I don't know how many hundreds of kilometers of lines he did with the quad, but this is the kind of data set that you get over the whole valley. So every point here is a vertical sounding where we have estimated resistivity after inversion. So you see the valley. We cannot go everywhere because there are villages, there are roads, there are trains, whatever, but you see the problem. So we want to interpolate that. In addition, we have boreholes. So along the boreholes, we have information about the clay fraction. And this is what is the most interesting for us in hydrogeology. If there is clay, it's impermeable. If there is no clay, it's permeable. So we have the clay fraction in the boreholes, and the boreholes are in the cities, and we have the resistivity data in general somewhere else in the fields. There are some points where we have both, so we can make a function that transforms resistivity into clay fraction. I'm not describing that. This is a lot of work, but in the end, we have the resistivity on all the black points. You can imagine a profile below. And we have the clay fraction estimated from the resistivity on the same locations, plus on the boreholes, the red points. And we had two variables for controlling the trends, the northing and the depths. So we have 4 variables, and what Alexis did also was to consider data uncertainty. I have no time to talk about that, but we have a very dense data set that looks like that. So what we do is just to apply MPS to fill the gaps, to model everything that is in between. And in the end, we have many simulations. This is what we get. The mean clay fraction on top, and below the uncertainty. And this was so exciting, because now we can make cross-sections everywhere in the valley and compare with what the Swiss Geological Survey interpolation was doing a few years ago. And so on the right, you have our estimation of clay fraction. So blue is mainly clay, brown, no, it's mainly aquifer. Brown is clay, sorry, and the white indicates the uncertainty. So when it becomes really white, it means that we have a large uncertainty we don't know. And you see that in some places it's very similar, the first section, for example. In other places, very different. But the most exciting thing was this one. So Alexis played the game to predict the clay fraction at a location where they were drilling, a new borehole was drilled. And we had no idea about the situation. So we are far, you see, this is the location of the borehole. We are far from the closer geophysical data. There is no other borehole at proximity. And this is the prediction. Clay fraction with uncertainty. On the right, you have the old prediction by the Swiss Geological Survey, saying that we should have an aquifer, we should have gravel at high depths. We predict that it is very certain that there will be clay, and on the bottom, we don't know, there is high uncertainty. And this is the borehole data. So, okay, that's one example out of how many. Maybe we were just lucky, but we were super happy. So, multi-resolution simulation. How much time do we have? 5 minutes, well. So this is something that we did with Tatiana. I don't know if Tatiana is here, Shugonova. Sometimes we were getting bad simulations. So you see here a training data set, you see a simulation, and we are missing some features. We have the big picture, but it was not so good. So we said maybe we can improve it using this multivariate framework again. So the idea was to use what is called Gaussian pyramids. How does it work? We first take the training data and we apply a kernel. It's a Gaussian kernel, it's convolution, you get a reduced image, lower resolution and smoothed out. Here it's black and white, or green and white, and here you have continuous values. The nice thing with Gaussian pyramids, you all experience Gaussian pyramids. If you go in Google Earth, you can zoom in, zoom out, and this is based on Gaussian pyramids. And so there is the reduce operation that creates a reduced image, but you have also the expand operation that goes in the other direction. So if you have a reduced image, you can create a high resolution, but very smooth initial image, but this is very fast because this is just convolution. We apply a Gaussian filter. So our idea was to take the initial training data. It's here, level 0 initial image. We smooth it, we get a lower resolution image, level 1. But we can expand it. So now we have, at this resolution, we have two images, the real one and the blurred one. And at the level above, we do the same. We reduce again and expand again. So now we have every time two images, the initial and the blurred one. And we have a pyramid because we can have many levels of this. So the trick now in the simulation is to start from the coarse resolution. So we start taking this image on top as a training image, and we make a simulation at coarse resolution. Exactly. But we have the operator that is super fast that can expand the image. So we can go from this coarse resolution, small image, to a higher resolution, but smoothed image very rapidly. And now we are in a situation where we can do multivariate MPS again. Because we have these two images here on the right that are the training data. Here we have the smoothed version, which is used as conditioning data, and we can simulate the finer image, but it's guided by the smoothed version. And we repeat. We are a bit stupid, we always repeat things. And in the end, you see the simulation is much better. So we compare the statistics, and that is really much better. It's not the end of everything. There are still issues, but I will not show them today. Why I show you that is because we are many to be interested in inverse problems, and inverse problems are much easier to solve when you work in a field that is continuous and of low dimension. So here, by creating this pyramid of images at different resolutions and smoother images, we have a mean now to control the fine categorical and high-dimensional image by a smooth, low-resolution version. So we can work on this image on top here. Maybe you can show it. Yeah. And work on the inversion at that level to make the adjustment, and then resimulate the rest very fast. And when we want to compute the forward response, we can do it on the high-resolution image, but we can do the perturbation on the top image. And this is a trick that was used by one of our PhD students, Dan Thuilam, and it seems to work pretty nicely. So we do the update with ensemble Kalman filters on the low-resolution images. We generate the categorical MPS simulations, and we do the inversion loop. So now this is just a teaser. This multivariate, multi-resolution ideas has been extended recently to work on unstructured grids. Unstructured grids are super for solving partial differential equations, but they are a nightmare for geostatistics because you are mixing up all kinds of support scales. The statistics depend on the scales. You have correlations between different scales, so it's difficult. But working with this multivariate, we were able to make an approximation and develop an algorithm that is capable of generating directly simulations on an unstructured grid, taking into account the support effect. And this is, as I said, a teaser, so Julien will show that in detail on Thursday. So summary and conclusion. I hope you remember the most important. DS, direct sampling, you have to pronounce it DS and not DC. we made this game of word, DS, in goddess, with direct sampling, and then everybody is pronouncing DS, DC, and so please remember, DS is direct sampling. Is an iterative conditional resampling of a training data set. I don't say training image anymore, because training data can be anything, can be time series, can be a lot of things, and it's not an image. So iterative conditional resampling of training data set. It's one flexible way of putting your prior knowledge into interpolation. And that's interesting because the classical geostatistics went all the way from estimation to simulation progressively. And we are doing the opposite. So we started with simulation, and progressively we are adding everything. Simulation about resonance stationarity, inequality, multi-resolution, support effect, and even estimation. And this will be shown by Thomas Meyer-Hansen and his colleagues. This is not our work, on Thursday as well. So we have a full palette of tools around MPS, and I think this is exciting. But now come the works. I mean, will we use MPS in 10 years? I don't know. Maybe we will be using GAN, and everybody is excited about GAN. So this is a new vehicle to provide prior information into our simulations, and I wonder who will run this race. So there are plenty of talks also about that. So that's it for me, and I am happy to answer questions if you have any.
Thank you so much, Philippe.
Thanks.
Any questions from the audience?
Yes.
Okay, thank you. I'm not an expert at all in the field, but what I really wonder is about those images, initial images that you use to complete the data set, training images. From what I understand, it's really important because it's kind of a bias based on other observations that will determine what the final result looks like. Is it right?
I have difficulty to hear you, so maybe can you repeat?
Can you speak in the microphone as well?
Sorry, yeah, same story. I had difficulties to understand and listen because there were noise and
All right. My question is, how important is a training image? Because it is the basis of this model, and if it is a bias that is based on natural observation, I suppose.
So I don't have it here, but yeah, the importance of the training data is less than we thought initially. So initially, we thought the training data is very important, and we want to simulate the training data. You see the first image by Sébastien Strebel. He was very careful about reproducing exactly the patterns that he had in the training image. But now what we realized is that the simulation is often, we want it to be different from the training image or training data set. And so we have to add some, and we had a lot of flexibility. You have seen the example of the Roussillon. We want it to turn, we want to change the size of the objects, we want to have other features, and so we have something that is called invariance. So we can consider that two patterns are identical up to a certain invariance. So we can have a tolerance on the pattern size. So the training image or the training data set is one ingredient, but because of all the other ingredients, usually we don't expect that the simulation should look like the training data. And even often very simple training data sets like stripes or squares or gives a really good simulations. And the only way to be sure in the end is to do some cross-validation. So if I would have an hour or two, I would also have spent cross-validation, but in the end, we have to cross-validate, yeah, and this is important. And I don't know if I answered properly to your answer. Yeah. Thanks.
Thanks. You talked quite a lot about the prior part, like forming geological realism. You did maybe not talk so much about the distance and these thresholds when you try to match the data.
Yeah.
Like the likelihood part. Is it sensitive to your T's or your distances?
Yes, very much. But not only the distance, because we have also the scan fraction. If we tend now to put very low distance and low scan fraction, so the algorithm is faster and gives more variability in the simulations. So when I say cross-validation, in the end, this is the important part, because we do cross-validation, we compare, and we want not only to have low errors, but we want to have a good estimation of the uncertainty. And this we can test with sharpness and calibration, and I think this is where we should go. I mean, we should predict statistically the things properly. Yeah. Thank you.
Okay. Thank you, Philippe. I think in the interest of time and in the coffee break, we're going to thank you again.
Thank you.
Stay here. Stay here because Peter Dowd, the president of the IAMG, will have a formal, and with some pictures, I guess, we'll have a formal award to deliver to you.
So we need to be on the side.
I'll just say that first. I think we've just heard an excellent example of Philippe's ability to convey complex concepts to a wide audience, and a perfect example of why he was chosen as the 2022 John Cedric Griffiths Teaching Awardee. Congratulations and very well done.
Merci beaucoup.
Thanks a lot.
Once again, thank you so much.